Hello, welcome to the second lecture of our course, which has the title Design of 100% of Grid Renewable Energy System. And we will be focusing in this lecture on the photovoltaic technology or the photovoltaic solutions. So we are going to size and design 100% of grid PV system to feed a community. Before we go for the procedure that we are going to follow in order to size the PV system to feed a community, let me try to illustrate you the PV system components. For sure, you know that we are going to have the PV array, which converts the sunlight to electricity. There are panels and we connected in series and parallel to form a PV array that will produce the electricity but in DC basis. And then we have a charge controller which usually stabilizes the voltage in order to charge a battery system. And sometimes we use energy that's stored in the battery system to feed the loads that we need. And of course, we have DC loads and we have AC loads. In order to convert the DC power produced from the PV system to AC power to be used in our homes, we need an inverter which converts the DC power to AC power in order to cope with our system and our consumption in our home. And even if you are going, as we will illustrate in the next lecture, if we are going to connect the PV system to the grid, we may use also an inverter because all the grids are AC grids now, and we need to convert the DC generation of the photovoltaics from DC to AC. In fact, sometimes we use auxiliary diesel generator, but since we are focusing on how to turn our communities to 100% renewable energy, we are not going to use those auxiliary diesel generators. So we will be working and depending on the PV as source of electricity production from sun, and the battery storage system that we are going to store the energy in while we have excess energy, and it will feed the demand when we have a reduction in our generation to feed our consumption. And we assume in this lecture that we are in a standalone, isolated community which is not connected to the grid. The sizing steps that we are going to follow in order to design and size a 100% off-grid PV system are going to determine first the active power consumption demands that we need to feed it by the 100% PV system. And then we are going to size the PV array that we need to have it in order to generate electricity from the sun. And then we are going to size the inverter and then size the battery. And finally, we are going to size the solar charger controller. Sometimes people are naming the solar charge controller as DC-DC converter. It has the same meaning. It just stabilizes the DC voltage produced from the PV to a certain amount of voltage, 12 volt, 24 volt, 48 volt, and sometimes maybe in electric cars or so on, 96 volt. Well, in order to determine the active power consumption demand, we need to set the objective, which is to find out the total power and energy consumption of all loads that need to be supplied by the solar PV system. The steps that we are going to follow is to calculate the total energy consumption per day, total watt hour per day for each appliance used, or each load used. And then we are going to multiply it by 1.3 in order to have safety factor considered in our PV power demand, because we are not sure that our demand will not increase, or even there will be enough sun to cover our consumption. So we usually add those 30% as safety margin. Let's have an example to make the image better. We have a house which has the following AC electric appliance usage: 118-watt fluorescent lamp with electronic ballast used 44 hours per day, 160-watt fan used for 2 hours per day, 175-watt refrigerator that runs 24 hours per day with compressor runs 12 hours and off 12 hours. In fact, we have to know that any load should be allowed to operate during the daylight or even at night when there is no sun. Here is the calculation of the PV load. We created a spreadsheet of the loads that we have. We have the fluorescent lamp. The unit of it has 18 watt. We have only one, and it's working 4 hours. So the total power is 18, and the energy needed to operate this fluorescent lamp is the power multiplied by the number of hours operated in, which is 4 hours. So it will be 72 watt hour per day. We have a fan, which is 60 watt, and it's one fan, which is working 2 hours per day. In fact, it will be 60 watt, and since it's working 2 hours, the energy will be the power multiplied by the time, which is 6 times 2, 120 watt hour per day. We have a fridge which is 75 watt, and it's one fridge that we have it. It's working. A compressor which draws electricity is working 12 hours per day. So we need energy 900 watt hour per day in order to operate the compressor of the fridge 12 hours a day as required. So the total energy is 1092 of those loads consumed a day. And you can say, because you need to put yourself in the safe side, that you are going to multiply it by 1.3. So it's going to be 1419.6 watt hour per day is required to be supplied by the PV systems that we are going to size in order to operate such loads of this house. To size the PV, you need to know a scientific word which we name it panel generation factor. As you can see here, the panel generation factor, which has the abbreviation PGF. In fact, the PGF is, sometimes they name it peak sun hours in the non-technically said words, which is simply, as I will tell you now, you can usually find that if this is the time and this is the power produced by the PV, it will be along the day like this, and this area is the energy produced by the PV. In fact, we are going to have the same energy, but in a rectangular shape like this. This is the peak power of the PV array. And this is the peak sun hours of the day. or PGF, as we name it technically as PGF. We use this technique in order to size easily the PV system, and each location worldwide and each site has a certain PGF. For example, here in Egypt, our PGF is ranging in all our locations from 4 to 5. In Europe, it's a little bit from 2.5 to 3.5. It depends upon your site, but in your site, it's easily to know the peaks and hours or the panel generation factor of your site. So what we are going to know is that the total watt peak rating of the PV array is the total watt hours per day needed from the PV array divided by the panel generation factor, which you already know about your site. And then we will need to know how many modules we need, which is the total watt peak rating of the PV array that we calculated in the previous step, divided by the rated power of the selected PV module, the one module rated power. We will use it as a maximum power. In case of any fractional that will be calculated in the number of modules, we are going to approximate it to the greater or the bigger number. For example, if they are 9.8, then we are going to have 10 modules, because we usually go for the safe scenario, not the less scenario, to keep ourselves in a reliable operation of our system, especially that we are working in 100% PV system. Here is the symbols of this equation that illustrates what is the PGF in a mathematical way. The following points are important to follow. The estimated number of PV modules is a minimum. If more PV modules are installed, the system will perform better and the battery life will be improved. Why is this? Because you are not going to use more power from the battery. You are just going to charge it till it charge it and it's done. So you are not going to use it much time. Then the battery will live more time with you, and you are going to increase the lifetime of the battery. If fewer PV modules are used, the system may not work at all during cloudy periods. There are days which called autonomy days where there is no sunlight, you can say so. At those days, your system will not be feeding your load, and the battery life will be shortened, since you are going to rely more on the charging and discharging of the battery, and this reduce the lifetime of the battery. We are going to assume for our example that we are in a site that has the panel generation factor 3.43, and we are going to use a module with 12 volt DC, 110 peak power, 110 watt peak power. We are going to use this type of PV. So we need to know what is the minimum number of the required modules. As we knew that we have 1419.6 watt hour energy needed from the PV to cover our consumption. Considering the 30% safety factor, we are going to divide this number by the PGF of the location, which is 3.43. Then we are going to have the total watt peak rating of the PV array. It will be 413.8776 watt. We are going to divide this number by the rated power of the PV module, or the maximum power of each module. We said that we are going to have a, as mentioned, 110 watt peak. So we are going to divide this number by 110. It will be 3.76, which are the number of the PV modules needed, and we have to buy it in order to get the required energy from the PV system. As we mentioned, when we have fraction, we have to approximate it to a greater number. So we are going to have 4 modules of this 110 watt peak module to cover the 1419.6 energy consumption of your demand, in addition to the safety factor. Those were the steps to optimally size the PV modules that you are going to buy in order to have 100% PV system. For the inverter, you need the input of the inverter to be greater than the total watt of the AC appliances. The inverter must have the same nominal voltage as your battery DC side from the DC side. So we will know what is the voltage of the battery that we are going to use in the next step. But in this step, we have to select the power of the inverter needed. We have 2 types of loads: static loads, which are mainly the lighting loads, and motor or compressor loads, which are the rotating loads. For the static loads, we just multiply it by 1.25 as a safety factor. And for the rotating loads, we multiplied it by 3 in order to avoid problems that happened during the starting of the rotating or the motor loads of some machines, compressors, in terms of fridges, and many other rotating machines, fans, for example, in this example. So we have a static load here, 18 watt of the fluorescent lamp, and we have 60 watt and 75 watt as motor loads. So we have 135 of motor loads, and we have 18 watt of static loads. So the inverter size should be greater than 1.25 multiplied by 18 as a static load, plus 3 multiplied by 135 as motor loads. So we are going to have at least 42.7 for 427.5 watt as the minimum size of the inverter. So our inverter should be greater than this number in a way or another. Mostly there is no inverter with 427.5 watts, so we are going to have it like 430 or 440, 450 watt inverter. Or usually half kilowatt inverter is good in such situation, and it's found in the market. For the battery sizing, you have to know that the average efficiency of most of the deep cycle batteries are 85%. And you can say that most of the people are using the deep cycle batteries in solar PV systems. And the depth of discharge is usually ranges between 60% and 80%. You have to consider that at night, the battery is the main source of electricity. If you are going to have 100% PV system in a location, and also in cloudy days, the battery will play a bigger role in feeding the demand. And as I mentioned, there are days when there is no sun. Those days are called days of autonomy, and somehow they are continuous days. For example, 2 or 3 days, very weak sun you are going to have in your site in deep winter, as we see in January and February in some countries. To make the task easy, we are going to follow this law, which is how to calculate the ampere hour of the battery capacity. It will be the total watt hours per day used by the appliances, total energy that we are going to have in our consumption, multiplied by the days of autonomy, the days, the continuous days that we are not going to have sun, divided by the efficiency, multiplied by the depth of discharge, and the nominal battery voltage. The nominal battery voltage is either 12, 24, or 48. It's one of those three options: 12, 24, or 48. The total appliances, as we calculated it, is 18 watt multiplied by 4 for the fluorescent lamp, 60 watt multiplied by 2 for the fan, 75 watt multiplied by 12 for the fridge and the compressor in the fridge. The nominal battery voltage here, as I mentioned, we are going to use it as 12. We could use it as 24 or 48. We will see how to select the optimal battery voltage or system voltage of the DC side. We assume the days of autonomy of our location 3 days. In fact, it depends. Here in Egypt, we assume it 1 or 2 days. In Europe, I think there are maybe 5 or 6 days. It depends upon the location. And then we calculated the ampere hour required for the battery, which is 535.29 ampere hour for 3 autonomy days. To buy it, we need 12 volt battery with 600 ampere hour, as we are going to approximate the 535.29 ampere hour to something that we could find in the market. Guidelines to select the battery voltage is if you are working in less than 1 kilowatt hour, then you have to use 12 volt system voltage. If you are working below 4 kilowatt hour, you may use 24 volt system voltage. If you are working in more than 4 kilowatt hour, you go for the 48 system voltage. It depends upon the total appliances of your house or the place that you are going to size to reach 100% renewable energy community. It varies, but usually we follow this procedure. The final equipment that we are going to size now is the charge controller. There are 2 types of charge controllers, in fact. The charge controller which do not have the option of maximum power point tracking, so it's not a track for the maximum power. We size it in an easy way. It has the voltage of the DC side, which if it's 12 for the battery, then it will be 12. If it's 24 for the battery, it will be 24. If it's 48, it will be 48. And we need to calculate the current or the current rating of the solar charge controller. It's usually 1.3 multiplied by the I short circuit of the PV array. Here is the specification of the PV modules that we have. The I short circuit is 7.5, as you see. So we are going to have the system, as I mentioned, is 12 volt. And since we have 4 series modules, then we are going to multiply the I short circuit by 4. So it will be 30 ampere I short circuit. Then we are going to have the rating of the charge controller 1.3. And usually this increase in the 30% is for safety factor multiplied by 30, the I short circuit of the PV module. It will be 39 ampere. Then we go and buy 12 volt, 39 ampere charge controller from the market. If we are going to have the second type of the charge controller, which is working to achieve the maximum power and has the option of maximum power point tracking, then the law will vary in the way that you will see now. The charge current rating will be 1.2 multiplied by the PV array watt peak divided by the nominal battery voltage, and the maximum power point voltage rating will be the open circuit voltage of the PV array. Let us see how in our example. The charge controller current rating will be 1.2, and usually this 20% is a safety factor, multiplied by 440, since the module has a watt peak of 110 and we have 4 modules, then we are going to have watt peak for the array of 440 divided by 12. It will be 44 ampere, and for the voltage it will be the open circuit voltage of the array. Since we have 4 modules connected in series, then we multiply 4 by the open circuit voltage of the module. It will be 4 multiplied by 20.7, which is 82.8 voltage. We worked a lot in many communities in order to turn it to be working with 100% renewable energy. We worked in solar pumping projects in the desert, where you can find it's working from standalone, and we did irrigation in such locations from only PV systems in an isolated mode. We worked in a 150 kilowatt solar pumping project in the desert of Oasis in Egypt here, and we did this irrigation in the morning by using PV without storage. This 150 kilowatt PV without storage, we installed it as you see in the desert in such a way. And we did that with students from my university, and we tested the inverter, as you can see here, and we test each part of the distribution box of the system, and we got the success moment when there is water from the underground of this desert in the oasis is up to irrigate the desert and turns the desert to green community. We worked in a project on how to do this irrigation, but at this time, not in the morning, we need to do it at night. So we came to the question, can we irrigate at night using PV? Because from agriculture point of view, this is useful for the planets to irrigate at night. The answer is yes, but in this occasion, you are going to rely more on your storage. So can we size it? Here is the load that is required to find a generation for it. We have a 1 kilowatt 5 motors. We have 1 kilowatt 5 motors working 5 hours per day, but we here multiplying the working hours in order to keep the battery lifetime more, and we calculated the energy in kilowatt hours. It will be 50 on this occasion. We have 2 pumps, one pump which will get the water from the underground, which is the main pump. It's 115 kilowatt pump. It's one pump, and we assume it will be working 10 hours per day. So we need 1,150 kilowatt hour. And we have another pump which has a task to lift up the water from the ground to the pivot, which is going to rotate through the motors, the 5 motors here, to irrigate the location, to reclaim the desert and turn it to a green community. Since we are going to have this with the battery, so we multiplied the working time of it. It will work only 5 hours, but we assumed here 10 in order to save our batteries, and we assume that we need energy in kilowatt hour of 370 for pump number 2, which will lift the water from the ground to the pivot that is going to irrigate. So we need total energy of 1570 kilowatt hour. In order to reduce the battery that we needed, we have a working strategy, which is, let me say, a smart working strategy a little bit. We don't get the water from the underground at night. We get it in the morning, depending on the PV only. So pump 1 is going to work in the morning, depending on the PV only, to get the water from the underground. Pump 2 and the motors, which are mainly used in the irrigation process, are going to work at night. So we achieve our target, which is irrigation at night, but we get the water from the underground in the morning. The real hours of working is 5 hours, but as I mentioned, we calculated for 10 in order to increase the lifetime of our batteries. Here is the sizing with a little bit the cost of the project. The project is now done and working. The panel generation factor of El Wahad is almost 5. As I mentioned, in Egypt here it's from 4 to 5, and this is a desert, so it's 5. So the power required from the PV is the total energy divided by the panel generation factor. So we need near 300 kilowatt, which means that we need 600 panels from the 500 watt type panel, the half kilowatt panel, which is already in the market. We have it in this project. The inverter required is 3 multiplied by 8.952 plus 115, which is 300 kilowatt. Here we considered the starting, so multiplied by 3, as mentioned in previous slides in the presentation. And for the battery, we need the energy divided by the DOD and the efficiency. So we need, if we are going for 24 voltage, we need 18 kilo ampere hour voltage, which is total 420 kilowatt hour. Total energy is required to operate pump 2 and the motors, and at night is 100 kilowatt hour. The DOD is assumed to be 50% through stabilizing the working hours of the pivot. As I mentioned, we assumed it's working 10 hours, but in fact it will work only 5 hours. And the efficiency in all cases is assumed to be 80%. The cost of the PV modules, here the 1 kilowatt of the PV modules usually costs 5,400 Egyptian pound, and we need 300 kilowatt, so it's 300 multiplied by 5,400 Egyptian pound, so it's 1,620,000 Egyptian pound. The inverter cost is the cost of the 100 kilowatt inverter from ABB, as an example, is 173,000 Egyptian pound. So we need 3 from the 100 kilowatt inverter, so it will cost 519,000 Egyptian pound. For the cost of the battery, In fact, the cost of the 10 kilowatt hour of battery is 15,600 Egyptian pound. So we need 42 of these because we need 420 kilowatt hour, as you can see here. So it will cost 655,000 Egyptian pound, as from this website. We get the cost of the 10 kilowatt hour of the battery. So the total cost of the project is going to be 2,794,000 Egyptian pound, which you can say with the change of the dollar and so on, it will turn to be 3 million Egyptian pound, which is not that big number to such project or big scale project. Now we turn to the second assignment of our course, and the assignment of this lecture is: can you size an off-grid renewable energy system to feed الواحات with such loads, those loads, with for irrigation at night also? So you consider that you irrigate at night using other sustainable technologies such as wind, biogas, biodiesel, geothermal, and assume what you like. You assume that there is this technology in such a place, and you may also use different energy storage facilities such as hydrogen, hydro pumped storage system, and so on. Please size for a different renewable energy technology and different energy storage facility. But you can use wind with the batteries, for example, biogas with the batteries. You can use, even if you assume that we are in a marine location, you can use waves or tides with the batteries, and feel free to use whatever you like, but try to size for an off-grid 100% renewable energy system to irrigate at night such demand. So you need 1570 kilowatt hour. At the end of this presentation, I would like to thank you very much and see you in the next lecture. Thank you.